Okay, so in the second part of section 9.3, we're going to compare the results from a significance test or hypothesis test, which is two-sided, to the results we would get from a confidence interval, and we'll see that they're very similar and relate it very directly. And then we'll also look at what happens if we have matched pair data and how we run a significance test using that data. All right. So when we did back at the last section, when we were talking about section 9.2, when we're doing proportions, we saw that a two-sided significance test for population proportions gave us similar results to when we did a confidence interval. So here we're going to see that if we do a significance test, a two-sided significance test, meaning we're going to be both the area in both tails, for population means, we get the exact same result that we would expect when we do a confidence interval. And the reason being here is that in both calculations that you can see here, we use S divided by the square root of n, S divided by the square root of n. So the standard error calculation is the same. For proportions, if you remember confidence intervals, we used p hats to calculate the standard error. And for the test statistic, the z statistic, we calculated it using hypothesized p values. So we got similar values, but slightly different. Here, for population means, you're going to see that they're exactly the same. All right, let's look at an example. The Hawaiian Pineapple Company installs a new watering system this year and wants to know if this year's pineapples have different weights from last year's. The mean weight from last year's was 31 ounces. The standard the statistician goes out into the field for this year's crop and picks 50 pineapples. All right. Then she runs statistics on that, a one sample t-test on it, and the results are listed here in like a little mini tab printout. So we can see the sample size is 50. We know, even though it's capital N, this particular software typically prints it out as capital, but that's the sample size, 50. The X bar, which is the mean, is 31.935. The standard deviation for the sample, so that's S, is 2.394. And then they go ahead and calculate the standard error as well. With the standard error would just be that standard deviation of 2.394 divided by the square root of 50. So they go ahead and do that, so you don't even have to calculate that if you don't want to. All right, so question A. Do these data give convincing evidence that the mean weight of pineapples this year has changed from last year's? All right, so you want to write your state. That's the null and alternative hypotheses. You also want to say the alpha level and what the mu stands for. So pause the video and write that. All right, so be careful with this. You have to read the question very carefully because up above it says they want to know if this year's have a different weight from last year's. Not more, not less, but different. So our alternative has got to be that the mu is not equal to 31. So you might think, without really reading the question too carefully, you might say, oh, there's a new watering system. Okay, the pineapples are going to be bigger this year because of that. But you have to run your test based on the question that they are asking. So they said, are the pineapples different from last year? So our alternative has to be that mu is not equal to 31. Okay, our alpha is 0.05. They didn't give us an alpha, so by default we use 0.05. And then we have to say what the mu is. It's the population mean weight of this year's pineapple. So you have to make sure that you're saying this year's pineapple, not the mean weight of all pineapples, because that would be last year and all the years before. So what's called into question is the mean weight of this year's pineapple. So, and again, we want to make sure that we say population mean weight so that we indicate that we're not talking about the 50 pineapples we picked, but all of the pineapples from this year's crop. All right, the plan. Again, what is your inference procedure and your 3 conditions? Write those out. Pause the video if you want. All right, so we do a 1 sample t-test for means. Remember that the calculator calls it just a t-test, but we want to say a 1 sample t-test for mu or for means. And then what are the conditions? We selected 50 random pineapples. We have to assume that this year's crop is more than 500 pineapples. And we have a sample size over 50, of 50, so that's more than 30. So central limit theorem tells us that our sampling distribution of x bar is approximately normal. Of course, we know it's going to follow a t distribution because when we actually do our calculations, we're substituting s for sigma. All right, and do your do. I would say do it in your calculator. Pause the video until you're finished. All right, so here I'm doing it by hand, but we can also do it in our calculators, doing a t-test. So when you do it in your calculator, make sure that you're giving the 4 things. So your answer, regardless really of which way you do it, should involve a response that involves the degrees of freedom, the t statistic, and the p-value along with a normal curve with shading. Well, a t-distribution with shading and labeling. Okay, so if you did it by hand, you get a statistic, a t-statistic of 2.76. Now remember, the p-value in this case is the probability that our t-statistic would be 2.76 or larger, or negative 2.76 or lower. So it's the probability that our statistic would take on a value as extreme or more extreme than the one it did, but in both directions from the mean. Because this is a 2-sided test, because remember, this is a not equal to. The alternative is not equal to, so that means we're in both tails, the shaded region in both tails. So our p-value is actually double. So if you're doing this by hand, we're going to get a t statistic of 2.76. Then we go and we have our degrees of freedom of 49, but of course we don't have 49 in our table, so we have to use line 40. And we see that the t statistic, 2.76, is between these 2 values. So we go up and read off these 2 p-values off the top of our table. However, we know this is a 2-sided test, so we would want to double those. Now, it depends on what table you're using. You might get slightly different values. Our table has slightly different columns, so you would get maybe slightly different values. All right. Also, if your table that you're using doesn't have a 2-tailed column heading, then you would just use the one tail heading and double it. So our table that we typically use has both one-sided and 2-sided table headings. So ours is 2-sided. So you want to make sure that you're using the right values. All right. So regardless of which way you do it, I mean, again, I would suggest doing this in your calculator using a t-test. Give me my 4 things: my degrees of freedom, t-statistic, p-value, or a range of those if you're using a t-table, but also the t-distribution, shaded, and labeling. And now your conclusion. Remember to have 3 components in your conclusion. Pause the video and write that out. All right, so 3 components here. The p-value is less than alpha. So the p-value of 0.0081 is less than or alpha of 0.05. The second thing we say is that we reject the null hypothesis. The third thing in our conclusion is that there is convincing evidence that the true mean weight of pineapples from this year's crop is different from 31. So again, you're taking the alternative hypothesis and saying it in words. All right, so the question B for this same question is, can we conclude that the new watering system caused any difference in the weights? And the answer is no. We did not do an experiment. We did not run a controlled experiment, so we cannot show causation. Perhaps this year's weather was warmer than last year. Perhaps there was more sunshine this year. There are other factors that could have come into play. We cannot show causation because we did not run a controlled experiment. So what we would want to do is randomly pick some fields and actually run the new watering system in some fields, and in other fields don't run the new watering system, and that way everything is the same as far as the weather, the sunshine, that kind of thing. The only thing difference is the watering system versus not watering system. All right. And then it asks us to verify the confidence interval from Minitab. So here we did the same example. The statistician, after running the t-test, used the pineapple data to run a confidence interval and ran that in a Minitab printout. So you can see here that we have the confidence interval listed. Right? It gives us the confidence interval. It also gave us the t statistic and p-value that we found in the last thing. So the Minitab will do lots of things for us. So what they want us to do is to use, you go back and do confidence intervals and calculate that confidence interval. Pause this video and try to do that on your own just to verify that confidence interval that Minitab gave us. All right, so we can do it by hand and using our formula that we saw back in section 8.3, x bar plus or minus the critical t value, s divided by square root of n. And you can see that indeed it gives us the same value that we got up above. And then it now asks us to correctly interpret the confidence interval, good practice for the next test. So pause the video and then write out your interpretation of the confidence interval. All right, so 3 components for this. We are 95% confident that the interval from 31.25 to 32.62 captures the true mean pineapple weights for this year's crop. So you got to make sure that you're specifically talking about this year's crop, not all pineapples, but this year's crop. All right, so the whole point of that example we just did and the results at the end that we wanted to look at is we rejected the null hypothesis. Also, notice that the hypothesized value of 31 was not in the 95% confidence interval. It was outside the interval. So those two outcomes are in agreement. So if we use an alpha level, say of 0.05, and we do a two-sided significance test like we did in that pineapple example, we rejected the null hypothesis, and also at a 95% confidence interval, we found that the hypothesized value 31 was not in our confidence interval. Remember, the confidence interval in part is a set of plausible values. All right, so when a two-sided significance test at an alpha level of alpha rejects H naught, then the one minus alpha, the 95 in our case, we had 0.05, so 5% alpha. 1 minus that would be a 95% confidence interval, does not contain the hypothesized value. So that's not a coincidence. That's always going to happen. All right, so when the two-sided significance test fails to reject the null hypothesis, the confidence interval will not contain mu, assuming, of course, that our alpha level and our confidence level are 1 minus each other. And we can see that same idea here if we open up the, I'm going to open up the Desmos and sort of talk about the same example here. Okay, so here is my Desmos file that I want to use to compare significance tests with confidence intervals. So here we have, this is from the pineapple example. So here we have the hypothesized mu value. So mu subscript 0 is set at 31. All right, so that is, we've drawn a vertical line there so we can kind of compare where that is. And so remember that this was a two-sided test. So I have my p-values indicated on the left side and on the right side. So those are the p-values. If my, I'm going to take a sample, and if that sample or x bar is sort of anywhere in this range, we're going to fail to reject the null hypothesis. If my x bar was out in this range, that means my p-value is smaller than alpha, and so we would reject the null hypothesis. Same thing out here. If my p-value, if my x bar was out in this range, we would reject the null hypothesis. Okay. So if instead of looking at just the x bar, what I did is I took the x bar and plotted my confidence interval around my x bar, I'd have something like this. So again, if my x bar is in this range, I'm going to fail to reject the null hypothesis. Notice I'm failing to reject the null hypothesis. The hypothesized value, mu sub naught, is contained in that blue confidence interval. If my p hat is just in the range where I'm going to reject my null hypothesis, notice that the hypothesized value is no longer contained in my confidence interval. So these things will always give us the same results. And over on this side too, if my x bar was low enough, then the hypothesized value is not contained in the confidence interval. So if you remember last chapter, we said as a test of a particular parameter value, we said, is it contained in our confidence interval? If it wasn't, then it wasn't a plausible value. This chapter, we're sort of saying, oh, we reject the null hypothesis, which is that hypothesized value. So if that again, if the x bar is in the middle here somewhere, then we're not rejecting the null hypothesis, and the hypothesized value 31 is in our confidence interval, so those things are in agreement. If it's out here far enough so that the x bar is far enough so that we would reject the null hypothesis, notice that the hypothesized value 31 is no longer in our confidence interval. And so that's what we're trying to talk about, is that the confidence intervals and this two-sided significance test give us the exact same results. All right, let's move on now to using paired data. So comparative studies are more convincing than single sample investigations. So for that reason, one sample inference is less common than comparative inference. Now we're going to get into that more in the later chapter, but for now we're going to talk about paired data. So study designs that involve making two observations on the same individual or on one observation on each of two similar individuals. This is paired data. When the data results from measuring the same quantitative variable twice, as in job satisfaction study, we can make comparisons by analyzing the differences in each pair. So we don't treat each set of data independently because they're not. They're not independent of each other. They're very related. So what we have to do is we have to look at the difference in the pairs of data. And so we call this a matched paired t test or a T procedure, a matched pair T procedure. We think of this as one sample because we're not taking two samples from two different populations. We're taking one sample, either the same individual or two very similar individuals, and we're subtracting the data. So it's the mean of the difference. We're not looking at the difference between the two means of the two sets of data because it's really just one set of data. All right, so remember what matched pairs look like. We saw this back in earlier chapter when we were talking about experimental design. So we have a pair of people, and so that pair, right, one pair of similar individuals, one of those two pairs gets put into treatment 1, the other gets put into treatment 2. So we have all these pair, treatment 1, all these different people that are in treatment 1, and all the different people in treatment 2. That way, we have we're guaranteed half of each pair of similar subjects is in E1 of each of the two treatments. Sort of another example of this is sometimes one subject gets two treatments, one after the other. And here, instead of randomly choosing one pair to go into one treatment and one pair to go in the other, the one subject gets randomly chosen, randomly selected which of the treatments they see first. But in this case, one subject gets both treatments. All right, so here's an example where we are going to look at paired data. Okay, so you have this on a Word document. It's a full page, like a worksheet on your PDF of these notes. All right, so here's the example. Does filling auto tires with nitrogen instead of compressed air reduce pressure loss over time? So, you all are starting to drive more. And so one thing that you have to do routinely on a car is check your air pressure. And so they're looking to see whether filling your tires with nitrogen reduces the air pressure loss over time. So you don't have to go fill up your air pressure as often. All right, so 10 different types of tires were chosen, one pair of each type. So two essentially identical tires. So tire number one, there are two identical type 1 tires. One is filled randomly chosen, right? Choose randomly which of the two identical tires gets filled with air, which one gets filled with 30 psi of nitrogen. All right, then all 20 tires. They do that for all 10 types of tires. So there's 20 different tires, 10 types, right? So there's two identical from each of the 10 types of tires. So each of the 20 then tires is placed outside for 1 year. And then at the end of 1 year, they go around to all 20 of them and measure the pressure. We call it air pressure, but in this case, it's nitrogen pressure, I guess. The pressure in the tire still. And then they record the numbers that they recorded is how much pressure loss it was. So rather than give us the PSI, this is how many PSI below 30 each tire was. So in this case, high numbers represent larger pressure loss. So the ideal situation here would be a very low number. That would mean that the tire did not lose much pressure. So for example, if we look at this one tire filled with nitrogen type 5, the nitrogen only lost 1 psi. Almost perfect, right? You lost almost none. Its twin, the one filled with air, lost 2.1 psi. So that tire actually did perform pretty well compared to some of the other ones. Tire number 1, type 1, in both cases lost about 7 psi in both cases. Okay. All right. So what we want to do is we want to decide whether the data gives convincing evidence at a significance level of 0.05 that filling the tire with nitrogen instead of air decreases pressure loss. All right. So we have this table again. You have this on a separate sheet of paper. I think what we want to do first is come up with our state. So you have to be careful with your state. In order to come up with this, we want to look at the difference data. We don't want to take the average of all 10 tires filled with air and the average pressure loss of all 10 tires filled with nitrogen. What we have to do is because those tires are not independent of each other. Those two tires are identical. Each of those pairs are identical tires. So we can't treat them as two separate samples. Instead, it's really sort of a sample of 10, not two samples of 10, but one sample of 10. And so we really want to come up with the difference data sort of first. And so we have to come up with, like, first of all, we have to think about how we're going to subtract. Are we going to say air minus nitrogen or nitrogen minus air? And it's kind of important because that's going to affect how we write our alternative hypothesis, right? So our null hypothesis is just that there is no difference, right? So the mean of the differences is going to be 0, right? So if we look at all the differences in all the data up here, if we look at fill in all these differences, that difference is going to be 0. Okay, so let's calculate those differences. So subtract each of those and then unpause the video when you're done. All right, so depending on how you subtracted them, I did air minus nitrogen. So then I have to say, because we think, the question is, right, it's how they ask the question, does filling the tire with nitrogen instead of air decrease pressure loss? So that means we would expect these numbers in our table to be higher for air than for nitrogen. That's what we're anticipating, and that's what was going to determine our alternative hypothesis. So the difference, which in my case I chose air minus nitrogen, dictates that my mean subscript D, which is the mean of the differences, is going to be greater than 0. If you by chance did nitrogen minus air, then you have to say less than 0 for your alternative. Okay. It's kind of important sometimes when we're doing these matched pair that the way you subtract the data, because we're always going to subtract the data, is really important because it's got to agree with your alternative hypothesis. Okay, so we say that mu sub D is the true mean of the differences in the pressure loss. So you got to be careful. It's not the difference of the means, it's the mean of the differences. So we take the differences first and then add them up, divide by 10. So it's the mean of the differences. Now, again, it's also not the mean of the differences of just those 10 types of tires, but all such tires, right, in the population. So the true mean difference, if we were going to do this for all such tires, as opposed to just the 10 we had. All right, the plan, come up with the inference procedure, and then test your 3 conditions and unpause pause the video, write that out, and then come back to it. All right, so in this case, it's a 1 sample t-test for mu, but here it's kind of a special case, so we will often say a 1 sample paired t-test for mu. And to make emphasize that this mu is the mean of the differences, we'll put a subscript D on that mu sometimes. All right, and the conditions, we want to know that we randomly assign treatments. We didn't randomly pick tires this case because this is an experiment. So we randomly assign treatments to each pair of tires. We are not sampling here. We're doing an experiment, And so this is one of the first times we're using an experiment in a significance test. So because we're not sampling, we don't really have to worry about the sampling without replacement or the 10% condition. The independence doesn't come into play here. All right, and then we don't know anything about the population distribution, and our sample size is less than 30, it's 10. So we would need to graph the sample data to make sure that we don't have any outliers or strong skewness. Okay, so we take that data. You can either put their original data. You could have put the air data and the nitrogen data into list 1 and list 2. And then what you can do is go up and highlight the list 3, highlight the title list 3 in your calculator and type L1 minus L2. And that will take those two data lists and subtract them and create your difference data for you. But you might have just went ahead and one at a time subtracted those data values. So one way or another, you just put that difference data into a list in your calculator. All right, and then ask it to do what I would say is maybe a box plot. And you can see from the box plot that there are no, so what you want to say is that I graphed the sample data, difference data in a box plot, and there were no strong outliers or strong skewness. Any outliers or strong skewness. So it is safe to assume that the sampling distribution of X bar is approximately normal, or that it is safe to proceed with our t-distribution calculations. All right, do. So I would suggest that you do it in your calculator. You can do it by hand or use your t-test in your calculator. This is still called a t-test, even though it's difference data. The calculator is just going to use the difference data in there. So put list 1. You choose that you're going to use the data. Put the data in list 1 or whatever list that it's in. Indicate that. The alternative hypothesis mu is greater than mu naught, which is 0 in this case. All right, so we choose our data, and it gives us our t statistic and our p value. Make sure, again, that you're giving me those 4 things: the degrees of freedom, the t statistic, the p value, and a normal curve, t curve, shade it with labeling. All right, and now let's work on the conclusion. Write that out and then unpause the video when you're done. All right, 3 components. Our p-value, and I actually put it down sometimes, but here it's pretty small. Our p-value of 0.00047 is less than our alpha of 0.05. Therefore, we reject the null hypothesis. Is the second thing. And then the third thing is we have convincing evidence. The smaller p-value is, the stronger the evidence against the null hypothesis. So we might even say there is convincing evidence that the true mean difference, that is air minus mu, I minus nitrogen, in the tire pressures loss is more than 0. All right, so again, you're saying that you have strong convincing evidence of HA, but you want to say that in context. All right, so it's fairly simple sometimes to run these tests, especially if you're using your calculator. But there's a couple of points to keep track of, so that you're doing a wise job of using these t-tests correctly. So let's look at a couple of things. All right, so small significance levels, that means alpha levels, require stronger evidence to reject the null hypothesis. Higher power gives you a better chance of detecting the difference, sometimes referred to as the effect. That's the difference between the hypothesized value, the parameter value, and the alternative, the actual parameter value, when it actually exists. So higher power is a good thing there. And the third thing is at any significance level and desired power level, detecting a small difference between that null parameter value and alternative parameter value. Again, that's known as the effect size. So detecting small differences between there require much larger sample sizes. All right, so again, let's just kind of rethink. I'm not going to reopen the Desmos file, but just boils down to what do we need to increase our power? So remember the things that increase power. Increasing the sample size increases power. Increasing our alpha level increases power. And having a larger effect. Now, you can't generally change what the alternative value of this, if the true parameter is a certain value, well, it's that value, right? So you can't change what the sample, what the true parameter lifetime of a battery is, right? I mean, in the short term, unless you're a scientist and you're trying to improve the battery. But you as a statistician don't have the ability to change that alternative. But if the alternative value is very different from the hypothesized value, then that will increase the power. The bigger that effect size is, the bigger the power. All right, so some things to think about when we're using these significance t-tests wisely. So when a null hypothesis, so that's the null hypothesis, that there is no difference, that kind of thing, can be rejected at the usual alpha level, 0.05, sometimes 0.01, there is good evidence of a difference. So when we reject the null hypothesis at an alpha level of 0.05 or even smaller, that just means that there's good evidence that there actually is a difference, that the true parameter is probably not the null hypothesized value, but is different. All right, but that difference can be pretty small, especially when you have large samples. All right, so the difference might be statistically different, but it may be really so small that it may not be worth it, right? So in the battery example, for example, um, the difference in the lifespan of the battery of 30 hours and our sample size was 33.9. It wasn't significant, right? It wasn't statistically significant. If you took a larger sample and we got that same X bar, then it can be statistically significant just for the mere fact that you have a really large sample size. Remember, when you get a really large sample size, the sampling distribution gets narrower. And so as a result, that sometimes by itself can make the result significant, even if the X bar is really not that much bigger and the true value is really not that much bigger. And so it really doesn't matter too much, especially when you're talking about really large sample size. So you're talking about, if you take 1,000 subjects in an experiment, for example, you might have slightly fewer headaches, but is it worth the expense of developing this new headache medicine? All right, and then the last thing, and we have a little visual to help represent this, multiple analysis. So a statistical significant ought to mean that you found a difference that you were looking for. So it's wrong to just keep trying more and more different things. Like, oh, let's try this, and that's statistically significant. No, let's try this. And so here's a good example, a visual to help explain that. All right, so this might be kind of hard to read, but it says, we found no link between purple jelly beans and acne. The p-value is greater than 0.05. Okay, so there doesn't seem to be a link. All right, next one. Oh, we found no link between brown jelly beans and acne. Oh, okay. So the p-value is greater than 0.05, not statistically significant. Oh, third case. Oh, we found no link between pink jelly beans and cases of acne. Oh, the p-value is greater than 0.05. Okay, so we found no relationship between those. So if you keep doing that again and again and again, like if you think a jelly bean was going to help with acne, then one thing, That's one thing. But you can't just like try one thing. It's like, oh, that didn't work. Let's try another. So in this case, we tried 20 different colored jelly beans, and we found that green seems to have a link to acne. Oh, eating green jelly beans helps clear up acne, according to this study. Okay, so what's going on here, right? A 95% confidence. Well, that really means that we have an alpha of 0.05. So think about the alpha of 0.05. We're going to reject the null hypothesis 5% of the time. Well, that's 1 in 20. So you can see we had 20 different jelly beans. So what's going on here is that jelly beans really don't affect acne, but occasionally you're going to reject the null hypothesis and think, oh, jelly beans actually do something here. But that's just because 5% of the time you expect to get the wrong answer. You expect to reject the null hypothesis 5% of the time. So 1 in 20. So that's what's really going on here. If you think green jelly beans do something for acne, then test green jelly beans. Don't just keep running tests until you find one that's statistically significant, because you will. Probability tells us that 5% of the time, if you're doing an alpha level of 0.05, that 1 in 20 tests will show some significance, even though there isn't any. Okay, so your homework, we have 3 4-steppers this time, so 78, 80, and 81. This is due next class. Please make sure you're practicing your 4 steps. Use your 4 steps in 78, 80, and 81.